We've all heard of the Pythagorean theorem in high school, right? It simply states that a squared plus b squared will always be equal to c squared, but only in a right triangle, which is when you have at least, and most, one right angle in your triangle. This well-known theorem has been drilled in every student's mind. You might have wondered why that is, and the answer is quite simple. This theorem is quite powerful and enables easier proof of mathematics and physics theorem than without it. You also might have asked yourself, why is it that this theorem is true? In other words, why is it that a squared plus b squared is always equal to c squared? For you have some mathematical knowledge, you might have figured this out on your own. And for those who don't have the required knowledge, let me show it to you. A right triangle has a very special property, which has to do with the areas of squares which are raised to the triangle sides. In fact, this area will always add up. What this means is that the area of the square which has length a, plus the area of this square which has length b, will always be equal to the area of this square which has length c. And so we can build this formula out of it. A squared plus b squared is always equal to c squared. There you have it, your well-known Pythagorean theorem. This is basically where it comes from. Now some may have stopped there, but since you probably like mathematics if you're watching this video, I won't stop there. In fact, there's a very important question which has not been asked and which only waits to be answered. That question simply is the proof of the discussed property of right triangles. Even if we were to accept this property, we have to prove it. And that, my friend, is the most fascinating part of mathematics. Proofs. Fortunately for us, this proof is quite simple. In fact, we can prove this property out of this single picture. The first thing to do is to prove that the angle FBC is equal to the angle ABD. Let's call our angle FBA and DBC x, since they are both right angles, so they are equal. Let's also say that the value of the angle ABC is y. Now we want to find the value of the angle FBC and compare it to ABD in order to prove that they are equal. To do that, let's say FBC is Z and ABD is Z prime. We can see from the picture that Z is equal to x plus y, and that Z prime is also equal to x plus y. This means that Z is equal to Z prime, or in other words, that FBC is equal to ABD. We can then prove that since those sides and those sides are equal, and that FBC is equal to ABD, that the two triangles ABD and FBC are equal. The second step is more complicated, but I will make sure to get you to the other side of this proof without losing anyone. We wanted to prove that this area, BE, is equal to those two areas, GB plus HC. So we first have to divide our square BE in two sub-areas which will be equal to one of the two squares. Those two areas are BL and CL. In other words, we need to prove that BL is equal to GB, since it is a smaller part, and that CL is equal to HC. To do so, we use a triangle we previously proved having the same area. We can prove that the area of the triangle ABD is half the area of the rectangle BL. To do so, let's assume that the base of ABD is BD. This base also is the base of BL. We know that the area of a rectangle is base times height, and that a triangle is base times height over 2. So let's just call BH A, which is the area of the rectangle. We know that the height of the rectangle BL is DL. The triangle also has the same height DL, as it is perpendicular to its base. Because of that, we can say that the area of the triangle ABD is equal to B times H over 2, or A over 2. We have therefore proved that the rectangle ABD is half the area of BL. This might seem like a useless thing to do, but This will enable us to compare the rectangle BL to the square GB, which is what we ultimately want. In fact, we proved that FBC is equal to ABD, and we also proved that ABD is half of BL. So FBC also is half of BL. Because of that, if we were to prove that the square GB is exactly 2 times the area of FBC, which is half of BL, then we could say that GB is equal to BL. To do so, we assume the base of FBC to be FB. This will also be the base of GB. We know that the area of a square is its sides squared, and so its area is FB squared. We also know that the height of the triangle is GF, since it is perpendicular to its base. Since GF is equal to FB, we can say that the area of the triangle FBC is FB squared divided by 2, meaning that the area of the square GB is twice the area of triangle FBC. Since we have proved that the triangle FBC is half the area of the rectangle BL and half the area of the square GB, it follows that the area of GB is equal to the area of BL. In order to prove that the square HC is equal to CL, we do the exact same kind of proof. I won't do it though, as it will only be repetitive, but if you want to know the complete proof, you should try to solve it yourself. Just do the exact same thing we did, or apply it to HC and CL. What an adventure! We just proved the Pythagorean theorem, which is not something everyone did. You can be proud of that. But we can still ask ourselves one last question. Is the Pythagorean theorem always true? As long as you're standing in front of a piece of paper and you wish to know the hypotenuse length of a right triangle, you should be alright. Also, as long as you want to know the distance between 2 relatively close points in space, you should also be alright. But let's say you wanted to know the distance between 2 faraway points on an Earth-like surface. It unfortunately will not work. You see, the Pythagorean theorem only works in what is called a Euclidean space, named in honor of its inventor, Euclid. You want to know what a Euclidean space is? Simply refer to your friendly Cartesian table on which you graphed all your linear curve, parabola, hyperbola, circle, etc. This is the perfect representation of a Euclidean space. If the Pythagorean theorem does not work, we call the space we are in a non-Euclidean space. A non-Euclidean space will be somewhat curved in a contrary to a Euclidean space which is completely flat or has what we call a Gaussian curvature of 0. Gaussian curvature simply is a measure of curvature. The best example of such space actually is space. Einstein's general relativity theory showed that the space is not a Euclidean space. It is in fact a non-Euclidean space because gravity actually bends the space around it. Instead it is curved. It is not a Euclidean space. But Einstein also said that when looking at relatively small distances, where the space also is uniformly bent, a Euclidean space is a good approximation of our space. So, our space is non-Euclidean, but it can be approximated to a Euclidean space when looking at small areas where the space is uniformly bent. For example, a small area on Earth's surfaces or in the Earth gravity field can be approximated to a Euclidean space, and in that case, the Pythagorean theorem will work. We can also look at a Euclidean space with a more mathematical definition. In fact, a Euclidean space is defined as a space in which Euclid's parallel postulate holds. In short, this postulate can be resumed to this. Let a line R and a point P not on R. There exists at most one line through P that does not intersect with R. In other words, there exists only one line which is parallel to R and goes through P. And in a non-Euclidean space, this postulate does not hold. For example, there exist two kinds of non-Euclidean space, which mathematicians have studied: an elliptic space, also called Riemannian space, and a hyperbolic space. In each space, they have different parallel postulate, and this is what makes them different by definition. In an elliptic space, parallel lines simply do not exist. Also, it differs in another weird way to Euclidean space. In fact, a triangle's sum will always be equal to 180 degrees in a Euclidean space, which is not the case in an elliptic space. In fact, a triangle's angle sum in an elliptic space will always be bigger than 180 degrees. In a hyperbolic space, the parallel postulate can be resumed to that. For a line R and a point P not on R, there exists at least two lines passing through P that do not intersect R. In other words, in a hyperbolic plane, a line has more than two parallel. Also, the angle sum of a triangle in a hyperbolic space is different from the other kind of space. In fact, it will always be smaller than 180 degrees. The fact that triangles do not have the same angle sum in different space sure is one of the reasons why Pythagorean theorem only works in a Euclidean space. There, you now know everything that there is to know about the Pythagorean theorem, or at least, that I do know. You might try to impress your friends, family, or math teachers with this new knowledge and look quite intelligent. Tell me in the comment if you liked or disliked this video so I can improve. And by the way, did you know that Pythagoras did not really discover the Pythagorean theorem? Some civilizations showed knowledge of this theorem before Pythagoras. And so the reason we remember this theorem as being his is still a big mystery. Who knows? Maybe he just wanted to be famous, right?